Hi, so today I will be talking about an experiment done by the SENSEI collaboration, which is titled Direct Detection Results on Sub-GeV Dark Matter from a New Skipper CCD. So first of all, the outline of my presentation will be as follows. First, I'll briefly explain dark matter and sub-GeV dark matter. Then I'll talk about the challenges of sub-GeV dark matter, the method used in this experiment, the experimental instrument, the data and the analysis of the data, and the findings from this experiment. And I'll briefly explain the findings and move to the future projects on this topic. So, first of all, what is dark matter? I believe that everyone has somewhat of an understanding of what dark matter is, but what we mostly know about it is, or at least what we suspect about it is, that it is non-baryonic, and that the universe is composed pretty much of 27% of dark matter. There are two popular theories of what dark matter really is. One is called WIMPs and the other is machos. WIMPs are essentially weakly interacting massive particles, which is some sort of a new elementary particle which is suspected to be even 1,000 times heavier than protons are. Machos, on the other hand, stand for massive compact halo objects. Machos are essentially any kind of astronomical bodies that might explain the presence of dark matter in galaxy halos. You might ask, how do we come up with these theories? How do we know that dark matter exists even though we can't see it? So there are two main conventional ways. One is due to the gravity's bending of light, which is also known as gravitational lensing. According to our observations, in the absence of dark matter, the bending of light will be significantly less, and therefore there should be some mass that accounts for the bending of light. Another observational evidence is galaxy clusters, because the mass of these clusters and the shape in which these clusters have formed would not be the way that it is right now in the absence of dark matter. Now, of course, these are all dark matter observations in very, very large scales that affect the distortion of light and the mass of galaxies. Now, what about sub-GeV dark matter? Well, the main issue with sub-GeV dark matter is it's harder to detect, the measurements are not very precise, and there is background radiation in the measurements, which really affects the accuracy of these measurements. Here, I will be delving into a bit of the theory behind the challenges of dark matter. So as you can see in this equation, the mass of dark matter squared is proportional to the momentum and therefore proportional to the recoil energy. And since sub-GeV dark matter is extremely small masses, and since the recoil energy is proportional to this mass, it becomes incredibly hard to detect the energy levels after mass of 10 GeV. Also, one thing that I want to make clear is what this recoil energy is and what it is used for. As you can evidently see from this equation, as I mentioned before, it is proportional to the dark matter mass. So it is a term that I will be using very often in this presentation, and it is basically what these scientists have been measuring to calculate the mass of dark matter. And you might ask, why do electron scattering if it's so hard to figure out the data? And that is because through electron scattering, we find the lowest thresholds of dark matter and lowest masses of dark matter. So that was the challenges of working with sub-GeV dark matter. Now I'll briefly mention the challenges of working with nuclear recoil. After a nuclear recoil, this energy is released as heat, light, in scintillation of photons, or as charge, as ionized atoms, or as electron-hole pairs, or as electron excitations. The main challenge in this is that, firstly, the calculations of heat can be very inaccurate, and also the charge and light yield for nuclear recoils below a few hundred EVs is not well understood, so the effects of that is not really calculated into the sub-GeV dark matter detection. This is sort of when the atomic Migdal effect kicks in. The Migdal effect is essentially the single electron scattering after a particle of dark matter scatters off of the nucleus. So what this helps with is that heat and the addition of charge and light is very hard to detect. However, the scattering of a single electron is much easier to detect, which really enhances the sensitivity of this dark matter recoil. So now I will talk about the instruments used in this experiment for a bit. So as you can see, the sub-electron noise skipper CCD experimental instrument is not very complex. The CCD stands for charge coupled devices, which is where the dark matter scattering occurs. Other than that, there's a copper base and copper exterior. And you can see that there is an extra lead shielding in the bottom where the electron exciting occurs. This extra lead shielding kind of works as an insulation property because since we have found evidence between a correlation between the rate of high energy background events and dark matter data, this extra lead shielding allows for the high rate background events to be minimized. So basically the sensitivity of this experiment is kind of dependent on the extra lead shielding. All of the other instruments are used for the flex circuit, and the LTA board are used for the controlling the electron scattering for the dark matter. First of all, before delving into the method, I want to mention that this experiment has been conducted 100 meters below ground for more muons to be detected. So now let's move on to the method of this experiment. First, as I mentioned, an electron is excited from the silicon valence band to the conduction band in one of the pixels of the skipper CCD. After the electron is excited, in the CCD module, dark matter and electron scattering occurs. Later, the charge in each pixel is then moved pixel to pixel to a readout stage located in one of the corners of the skipper CCD. The pixel charge is then measured repeatedly and non-destructively to sub-electron noise precision. And thus, many different types of data and many different observations emerge from this experiment. The first data table that I want to analyze is one of single electron event rate, also noted as R1-E, and background radiation. As I mentioned in the instruments, the extra lead shielding was proven to reduce background radiation, and this also, the correlation between background radiation and single electron event rate can be observed through this data. The line in red is the one with extra shielding. The line in green is the one with the amplifier off during the dark matter and electron exposure, and the line in black is the images with the amplifier on during the exposure. You can see where there is less background radiation with the extra shielding, there is a lower amount of single electron event rate than there is with the amplifier off and on without the extra shielding. These experimental results further back the hypothesis that there is a direct correlation between the background radiation and the dark matter observed. Next, we can see the data of the pixel charge spectra with a double Gaussian fit. Figure 3 is collected through dark matter that scatters off nuclei through the Migdal effect. Although current estimates of the Migdal effect at low recoil energies are uncertain, through this experiment the recoil energy was found to be 2.399 events per G-day, and there has been an upper limit that has been reduced from the past experiments due to the increased sensitivity in this experiment. Also, the data collected through the Migdal effect and the experiment is consistent with the other dark matter results. In the final part of the data section, we see 4 different data tables. The top left one being dark matter electron scattering for one form, and the top right one being dark matter electron scattering for another form. The bottom left one being dark matter neutron scattering through the Migdal effect, and the bottom left one being dark photon dark matter absorption. Through this, we observe new sign line upper limits on single, double, triple, and 4 electron events. And also, as seen on the sign solid line in these graphs, the upper limits of dark matter observation in these single, double, triple, and quadruple electron events have been observed with much more accurate and precise data up to 90% of the upper limits. In the data analysis section, there are a few things that we need to mention. We should acknowledge that during the analysis of this data, the SENSEI collaboration have removed images with a 30% or larger readout noise than the expected readout noise. Now we can move on to the findings of this experiment and what this really means. So first of all, one of the most important parts of this experiment was to reduce significantly the background noise in sub-GeV dark matter observation. The dependence of single electron rates on environmental backgrounds have effectively been supported through this experiment, and there has been a significant reduction in the effect of these environmental backgrounds on dark matter observation. Also, through this experiment, we have found that the observed rate of single electron events correlate with the shield thickness, as we have seen in the extra lead shielding, and also, therefore, the rate of background events that affect the detector. And finally, the upper limits for how many electrons per pixel per day could be attributed to different lightweight dark matter particles have been more effectively and more accurately determined. Also, one of the things that we can't exactly conclude but can expect from this experiment is that dark current contribution should be more than an order of magnitude lower than the observed recoil energy. Now, of course, these are all very good findings in terms of accuracy and precision. However, what does this all mean? Well, first of all, dark matter remains one of the mysteries in astroparticle physics and astrophysics. So getting more accurate data and getting more information about what affects the observation of dark matter, and also the fact that one electron event correlates with the rate of high energy background has been observed for the first time. So that is one of the most major findings. And not only are these the one of the most accurate results of dark matter, sub-GeV dark matter observation, but in a single electron event, this is the lowest rate ever measured in a single detector. For 2 electron events, it's also the lowest rate ever measured in a single detector, and it seems to disfavor a dark matter interpretation that excess events observed in the previous experiments. So finally, what's next about this experiment, about the SENSEI collaboration? First of all, they will be improving on previous detector limits, and they will be sort of repeating this experiment in better detector limits and better shielding to get even more accurate results. And in the new low radiation shield currently being built in the Snow Lab facility, there will be a phased approach for the Skipper CCDs, and this experiment will be repeated with around 50 of these instruments to get even lower and more accurate rates of recoil energy. It is planned to accumulate around 100 G years of exposure over the next 1 to 2 years. Direct detection of dark matter is extremely difficult. However, at least it seems a bit bright in the near future. Thank you for listening to me. I will answer any of your questions to the best of my abilities.